Buenos Aires, Argentina, not from Mallorca, that it was stated another mistake of the booklet, sorry. And the title of her talk is Topological Degree and Periodic Orbits of Semi-Dynamical Systems. So, Melanie, when you want.
Yeah, so it's already in presentation format. Perfect. So, well, first of all, thank you so much for inviting me to give this talk in this last minute presentation. And also thanks to the organizer for making this online workshop possible. I was super eager to participate, but you know, since I'm from Universidad de Buenos Aires and Imos CONICET, that is actually in Argentina, it was kind of hard to be in Barcelona at the time. But in any case, actually, at the present moment, I'm living in Italy, so we are in the same time zone. It's not like 5 hours earlier for me. So the title is Topological Degree and Periodic Orbits of Semi-Dynamical Systems. And the main idea is to show how topological techniques can be used to show the existence of closed orbits of dynamical systems. So with this setting, a brief outline is that the semi-dynamical system that I will consider is induced by delay differential equations. And because of that, I'm going to give a brief definition about topological degree and some tools in order to state the main result, that is the existence of periodic solutions. So with this in mind, our systems read x prime equals f of t x, x in t minus tau. And of course, since this last term involves all this information, where of course tau is a positive delay, in order to establish an initial condition, we need to say which is the value in the whole interval. So the initial condition is a continuous function in this space that is, of course, infinite dimensional. So in contrast with the OD theory, the semi-flow associated to the solutions of the system that, by the way, the solutions we are assuming that are uniquely defined and all over the real, the positive real line. So it's defined by x sub s, where x sub s on t is just x evaluated in t plus s. That, of course, induces a semi-dynamical system. So, well, with this setting, we are going to consider a topological degree. So the approach in the classic OD theory would be, when we want to search periodic orbits, would be like to consider a Poincaré map and to find fixed point of this operator via the Brouwer degree. But since the space is infinite dimensional, we cannot apply this technique. So we shall work with a generalization of the degree that is known as the LERAY-SCHAUDER degree. And so with this setting, we shall define in a brief moment a compact operator on a proper subset of C sub t, where C sub t is the Banach space of T periodic continuous functions. The idea is like, if f is T periodic, then the fixed point of this operator will determine the T periodic orbits of the system. So the whole idea is to define a proper operator and find a suitable set to be able to use the LERAY-SCHAUDER degree. So let's recall, or maybe just define what is the LERAY-SCHAUDER degree. So set just an U open bounded set and consider a compact operator such that it doesn't have any fixed point on the boundary end of U, and set epsilon as this infimum. So the LERAY-SCHAUDER degree of the identity minus k on U around 0 is defined as the Brouwer degree of identity minus chi sub epsilon restricted to B sub epsilon, where B sub epsilon is of course finite dimensional over this intersection around 0, where again k sub epsilon is an epsilon approximation of k with finite range. So the key is that if the LERAY-SCHAUDER degree of this operator is not 0, then the fixed point of k is non-empty. So this is the whole approach. So let's begin with the tools that are going to allow us to define this U proper set that we're going to work. So we will consider B a guiding function that verifies this inner product between the gradient of B against F to be positive around Bx, By lower than R sub 0, and such that the limit of B on X is 0 as the norm of X is going to 0. So this may be compared with Lyapunov mappings, but of course, instead of having this inequality, we would have one negative in this part. And it's also said like to be guiding type, since the classic theory of guiding functions involves other kind of sets. We are concerning to see the behavior or the dynamics of our flow or semi-flow in Bx lower than R sub 0, when in guiding functions we want to evaluate how is the behaviors on sets of the norm of X is greater than R sub 0. So, well, the main thing is that B will allow us to set which is the proper set to apply degree techniques. So in order to figure this out, let's start with some basic assumptions. You see H1, H2, and H3 that it may be like technicals, but this is like what I was mentioned before, that is our framework was a little wider than just assuming like showing existence of periodic orbits. We also analyze the notions of persistence and distributedness properties, where like we want to find lower bounds of the solutions. Precisely, H1s can be interpreted that if we start with a positive function, then H1 says that the solution will remain positive for all t. This is, of course, kind of obvious because it's just saying that if we begin with something non-zero and we end up with x sub j 0, then the derivative is going to be positive. The second one states some kind of B monotony around the inner product of the gradient of f against xy, and here x on the diagonal directly whenever we have this inequality. That is mainly because when you have delayed differential equations, one of the main problems where you can't use like fixed point operators or Schauder theorem is just like when you try to see the distance between the solution and the delay solution, you can't control this distance. So you need some kind of monotony in order to like bound this variation. So in fact, with these two hypotheses, one can find what is called uniform persistence, that basically says that all the solutions are uniformly bounded from below, and for all t, that is going to give us a lower bound in order to find our proper region to exactly use topological degree. The third one is to give an upper bound, that it says that if we have some constant bigger than r sub 0, where r sub 0 of course is this one. So we will ask that the inner product of the gradient of b against f is negative in this interval. This will guarantee that if the solution starts inside of this region, then the flow will remain inside for all t. So this is the whole idea that is going to be used in the sketch of the proof. So finally, we can state the main theorem of this talk, that says that if H1, H2, and H3 hold and F is t-periodic in the first coordinate, then there is at least a t-periodic positive orbit inside of omega, where omega, of course, is x in Rn, such Bx is in between R0 and R, provided that the Euler characteristic of omega is non-zero. Notice that this guiding function can be chosen depending the problem we are studying. We use different kind, but the most common could be like taking the Euclidean norm of Rn, and so this is immediately true, like this is verified without any question. So in order to prove the theorem, we are going to use this crucial result, that is the Hopf theorem, which states that if nu is the outward normal on omega, then the degree of B, the Brouwer degree of nu, is equal to the Euler characteristic of omega. So let's see a sketch of it. So to do this, let's introduce some notation. Let's set I of x, the integral operator, over line x, just the mean of this operator, and then n of x, just f of t x, xt minus tau, that is called as the enemy's key operator for the ones who knows it. So finally we set u, our important set, as the x on c sub t, a periodic continuous function such that x of t belongs inside of omega for all t. Again, where omega is this set, dependent of this guiding function. So finally, we can define our compact operator that goes from overline u to c sub t, and is well defined, meaning that k of x is t-periodic. It's super easy to see that, and also that is compact. It's just a simple computation. So what important thing to remark is that every fixed point of this operator is a solution of our equation, hence a periodic orbit of our semi-dynamical system. And conversely, every solution of our system is a fixed point of k. This is going to be crucial in the proof, that we are not going to see it like properly, but this is like the main thing to notice. So the idea is C Rn inside of C sub t using the constant functions, which implies that U intersected with Rn is omega, and then define another compact operator on C sub t that goes on Rn just because of this trivial definition, and consider nu. They were normal, but it's tended inside of omega. So now we consider linear homotopies, and we see that K is homotopic to K sub 0 in C sub t, with the important thing that it doesn't have any fixed point on the boundary of U. In order to prove this fact is where H1, H2, and H3 is super important, which it says that if a solution is inside of the region, it can't go out. So that is what is avoiding to have any problems on the boundary. And then we go down to Rn, projecting, and we see if the restricting K sub 0 to overline omega, we see that is homotopic to nu, that is equal to be homotopic to minus nu, is essentially to say that the flow is, the semi-flow is pointing inward in order to remain everything inside of the region. So with the same computation, one sees that it doesn't have any fixed point on the boundary of omega. So with this in mind, we can almost finish, because you know from invariance of the degree, you know that the LERAY-SCHAUDER degree of identity minus k on U around 0 will be the degree of the Brouwer degree of identity minus k sub 0 on omega around 0. That in turn is the Brouwer degree of minus the outward normal in omega around 0. And by Hopf theorem, this is plus or minus 1, the Euler characteristic of omega. And as I said before, if B is the Euclidean norm, this is trivially 1. So we get that this degree is non-zero. And to sum up, that means that the set of fixed points of K is non-empty, implying that ones have a exactly periodic solution. So this is like the main ideas, and so this is it. So thanks so much for your attention.
Okay, thank you, Melanie, for this very clear presentation.
Thank you.
And now it's time for